Curvilinear motion. This is the end of chapter 11, and this tends to be one of the more difficult subjects to get through for everybody. So I'm going to try and start with what you're familiar with. Don't glaze over when you see stuff that you're already familiar with, because we're going to build on that and just use that as a foundation. So we're going to start with just a basic review of vectors, what you have learned in statics and physics. And then we're going to build on that to pull that into rotational motion as well. We'll talk through normal and tangential vectors, and then we'll do various different types of rotational motion, whether it's a perfect circle, to the very end, your radius and angle is changing. Curvilinear motion, what are we talking about here? We're going to start looking at particles that aren't just traveling in the x direction, not just traveling in the y direction, but have some combination of both x and y motion going on. And this will create some sort of a curved path. And we're going to keep track of everything with the normal and tangent directions with respect to that curve. If you remember some of this stuff from your physics class, our accelerations are going to be broken up into tangential and normal directions as well, and we'll go through each of these components and where they come from here in the next few slides. Let me just review a few concepts about what vectors are. We had lots of vectors in physics and in statics. So here's an example vector problem. We have forces, got tension coming up, tension coming down, and you can take these three vectors, add them together as a triangle, head to tail. Realize that it's not just forces that have x and y components and are made of vectors. F equals ma. Acceleration is also a vector. Velocity is also a vector. Anything that is a vector, you can break into x and y components. You can add head to tail, head to tail. They're all just vectors. So everything you learned about adding forces together, you can now apply to adding accelerations together, adding velocities together, adding anything that is a vector together. So you're going to break everything up into x and y components. You can add them graphically by arranging them head to tail with one another. So let's just review what these vector things are, how they add, how you break them apart. Okay, so this is a triangle rule. When you add them head to tail, you're just going to align them. So remember, a vector has a magnitude, how long the thing is, and a direction, which way it's pointed at. Those are the two big components. You can add them on the right-hand side, on the left-hand side, so there's several different ways to add these things together. They both give the same resultant force, so call it a triangle or a parallelogram. It's the same thing. That's how you add vectors, whether it's an acceleration vector or velocity vector, they all add the same. So you just draw it out. Drawing the pictures on this and keeping track of angles, that's the important part for vectors. Okay, what if you know all of the angles in a problem, but you only know the length of one side? What would you do to solve for the lengths of the other side? Do you remember law of sines, law of cosines? Which one would you use, the law of sines or the law of cosines? So here you go. If you know all the angles and one side, which is what this is, that's going to be the law of sines. Okay, here's the law of sines. If you know two sides and an angle, that would be the law of cosines. I'll give you an example with that one too. Okay, so it's just the ratio, right? So 50 goes with 40, T2 goes with 30, T3 goes with 110. It's just the angle that's on the opposite side to each of those vectors. So that's a quick way to add them together. And again, this isn't just for forces. Any vector this will work with. So velocities, acceleration. Acceleration is what gives force its direction. So everything you learned with forces, you will now be applying to a few more vector ideas. Okay, so there's the law of sines. Very easy to walk around. Just use those ratios to solve for everything in that triangle. This is the way most people do vectors. You split it into x components and y components. Okay, and then you're going to add together everything in the x direction, and you add together everything in the y direction. And again, in dynamics, the only difference here is it's not going to add to 0. And whatever is left over in the x and y direction, that's going to be what accelerations are happening in the x and y direction. And something interesting to remember here too is that x is independent of y. So you can shove this around all you want in the x direction, and it's never going to change what's happening in the y direction. It's kind of an interesting thing. It's like two completely different problems. So you look at everything in the x direction, and that's its own little entity, and then independent of what's going on in the x direction, you have what's in the y direction. Kind of an odd thing. You'd think if you pushed hard enough in the x direction, something would happen in the y direction, but it doesn't. They're completely independent of one another. Just a strange sort of a thing. The next thing we're going to talk about is coordinate systems. There's a couple different types of coordinate systems. X and Y, what you're used to, normal and tangential. For some reason, there's always someone who's confused about normal and tangential coordinate systems. So I want to walk through and try and convince you that it's really pretty much the same thing. Okay, so let's go for the classic experiment. You have a block on an inclined plane, and you're going to see when it starts slipping. You're going to measure the friction coefficient or something, okay? So you make a free body diagram of the block. What's the forces acting on the block? You have weight coming down, mg coming down, normal force that is at right angles with that board. It's perpendicular to the board. And then you have friction that's resisting it, keeping it from sliding down the board. Okay, so we're going to make free body diagrams in dynamics, just like you did in physics, just like statics. The only difference is the forces aren't going to add to 0. It's going to look horribly lopsided and non-symmetrical. You get used to equal and opposite forces in statics. They're not equal and opposite anymore. The forces are not equal to one another. That's whatever is not balanced. That's what makes it move. So it's going to look kind of awkward for a while, and it is awkward and lopsided. But that's dynamics. Okay, how are we going to put some coordinates on here? Should we just keep our x and y coordinates horizontal? This is the traditional way, right? You always see x is horizontal and y is vertical. What would happen if we did this? Okay, so we can break everything into their x and y components. So there's our friction into x and y components. There's normal force into x and y components. Then gravity's all the way down. So there's a question we ask ourselves here: is there a better way to break these forces apart? So can you answer that? Is there a better way to do this? Okay, here we go. What if we orient the coordinate system in the normal and tangential direction instead? Is this better? Okay, so here we are. We only have one force to break into components this time around. Friction is all the way in the x direction. Normal force is all the way in the y direction. So orienting the coordinate like this is better. It's better because there's fewer things to break apart. Our motion is in the x direction, so now we don't have to break motion into x and y components. It just makes sense to orient your coordinate system in the same direction that motion is happening in the same direction that most of the forces are happening in. It keeps things simpler and easier to work through the problem. Okay, so I'm still calling this x and y. Could I label that something different? Could I call it Z and Q? Could I call it direction C and P? You can call it whatever you want, right? The idea is you're just breaking forces apart into perpendicular components. So whether you call it X and Y or normal and tangential, it's the same thing, okay? So either way, you're just breaking forces together into these perpendicular components. So what is perpendicular to this direction and what is lined up with it? We're looking for everything here in the normal direction, and we're looking for everything in the tangential direction. So call it x and y or call it t and n, it doesn't matter. Tangent and normal are just describing that we're we're now aligning ourselves with some surface, okay? So it's no different than x and y. If you can do stuff in x and y direction, you can do stuff in normal and tangential. So here we have how you typically see normal and tangential direction. Let's say you have a tennis ball on a string and you're swinging it around in a circle, okay? There's a lab exercise that you can play around doing this. In the circle, our velocity is always going to be in the tangent direction, and our acceleration is going to have a tangent and a normal component. So it's just easier and simpler to orient our coordinate system in the tangent and normal direction, okay? Same thing as the block on an inclined plane. The reason we're doing this is because this is where the accelerations happen, where the forces happen. It just makes life easier. But call it x and y or call it normal tangential, it's the same thing. You're just breaking forces or accelerations or velocities into these two directions. How much is in the normal direction, how much is in the tangent direction. Okay, normal acceleration, tangential acceleration. Has it been a while since you've been in physics? Let's just go over these concepts again. You've seen them before, but it takes about 5 times of seeing something before it really solidifies. That's what they say anyways. Okay, so what's acceleration anyways? It's change in velocity with change in time. There's our old equation, except there's something missing here. What is missing in this equation? What are we not showing here? When we were using this equation before, we were using it for rectilinear motion, linear motion. But now we don't have linear motion anymore. It's changing direction as well as magnitude, okay? This is a vector. There's 2 pieces to it, direction and magnitude. So now that we're going to be changing the direction too, we need to add something to it. We need to add something saying what direction it's in. Okay, so just like you'd break forces into IJK components, we're going to break this guy into components too, and it turns out velocity will always be tangent to the curve, and we can go through a proof for that too if you want to see it. But you'll never have normal velocity. Normal acceleration, yes, not normal velocity. Velocity is always tangent to the curve, so we have the magnitude of it, and then the direction is this little unit vector right here that we're going to add on to it. So when we take the derivative, see how these are changing with time. It's not just the magnitude that's changing with time, it's also the direction that's changing with time. So derivative of the first times the second, and the second times the derivative of the first. You just split each of these guys apart, okay? And then we're going to be looking at how the magnitude changes, okay? So you're swinging this tennis ball around in a circle, and you can swing it faster or slower. So if you go from 10 miles an hour around the curve to 20, if you go from 10 to 20 miles an hour, that's changing the magnitude, okay? That's this piece of it. But we're not just changing the magnitude, we're also changing the direction, okay? So if we're over here, tangent is up, and then that tangential direction changes as we're going around the curve. So that's the 2 pieces of velocity. What we're going to do here is another chain rule. We're going to split dE dt. We're going to add some angles in there. S is like x, okay? That's the arc length. So that's the distance that's traveled. And we're going to use this chain law for a couple different reasons. So here's all of the stuff that's in here. How is tangential direction changing with theta? Turns out it changes in the normal direction. What that ball wants to do is go flying off in a straight line, okay? And it's not going in a straight line. It's getting pulled back to the center. So the direction is getting pulled back to the center. This is how the direction changes. It just keeps getting pulled in and pulled in and pulled in. The next little piece, how is the angle changing with, instead of dx, it's ds. This is the arc length. Okay, and if you rearrange this, it ends up being rho or radius. This is like I should have called it an R for radius. So radius is ds d theta. This is like 2 pi r is the circumference of a circle. Okay, radius times the change in the angle, that's the arc length. So we have a radius, d theta equals ds, and this ends up being 1 divided by r. Last piece, ds dt, change in distance over change in time, well that's just velocity. So we have velocity here, v squared. We have radius, v squared over r. Is it starting to look familiar? And we have this happening in the normal direction. So this is the normal piece of the acceleration right here. So here we go. Acceleration, instead of breaking it into x and y components, it's tangential and normal components. The tangent piece of it is describing how the magnitude of the acceleration is changing. The normal component is describing how the direction is changing. So this guy is v squared over r, and this one is change in the magnitude with dt. Velocity is always tangent to the curve. Let's just walk through this idea. We'll start down here with what we're familiar with. V equals dx dt. So what are we talking about here? Dx dt. Let's do the vector analysis. So we have a ball starting out at some position 1. So at time 1, we're here. And some later time, we're here. So we're moving our position, okay? So let's say we identify where the position of 1 is with x, okay? So we're starting out at x1. Sometime later, we're now at position x2. And if we want to see how that has changed, it's the difference between these two vectors, okay? So the difference between x1 and x2 is dx. That's what's changing for our velocity with time. Okay, so that's a very simple example. Now let's switch it around a little bit. Same starting place. So here's position 1, here's position 2, only this time we are going to measure where they're at with respect to a new point. Okay, so I'm going to say 1 is being measured with this new vector, so we're looking at it with respect to a new starting point. So there's 1, there's 2, and here's the difference between those two vectors, okay? The dx versus ds, it's the same length. We're just measuring that difference from two different vectors. You remember how to add vectors, right? So if you have 3 vectors, a plus b equals c, okay? And you're just putting them together head to tail, that's how you add them together, and the resultant of those two would be c. So that's the same thing. We have position 1, and position 1, we're going to add to that how much the position changes, ds, that's how much it's changed, and then we get position 2 out of it, okay? It's the same sort of thing. So instead of a plus b equals c, we have position 1 plus how that position is changing, and that's our new spot. So let's map this out up onto a curve. So we're going around in some kind of a curved path, circular path. So we have position number 1. Okay, let's say we're starting out here, and sometime in the future we're now at position number 2. And so where has our position changed? So here is ds, okay? Instead of dx, it's ds. This is how the position is changing with time. Well, if we want to go to calculus and take smaller and smaller slivers of this now. So let's say position 1 is here and position 2 is here. So we have just this teeny little sliver going on, okay? As these vectors get closer and closer together, what direction is change in our arc length in, ds? What direction is ds in? Hopefully you can see that these skinny little slices of pizza, our ds goes tangent to the curve. So that's why our velocity is always tangent to the curve, is because of how we're just adding these vectors together. Okay, so velocity, and it makes it very easy that we always know the direction of it. It's always tangent. So if you connect the center to where your object is, just draw something perpendicular to that. Perpendicular to it, tangent to it, that's where velocity is going to be going. Let's talk about the case of circular motion. So not just any random arc or curved path, but we're going in a circle that has a radius. It's going to stay at the same radius. And in this case, we can define velocity based on the radius and how fast the angle is changing. This quantity is omega. So let's just define some vocabulary here and some symbols that are going to be used. First, here's a question. What is the circumference of a circle? Why am I asking this? You remember this, right? Circumference equals 2 pi r. Okay, how about we just want half of a circle? What would be the arc length of just half of a circle? Well, if the circumference is 2 pi r, then half of a circle would just be pi r, right? Okay, how about we just want a little piece of the circle, a little arc length? What would be the length of that arc there? Well, the arc length would be some angle times r. Okay, it's not 2 pi r or pi, it's just how far it's traveled. And this is the amazing thing about radians and pi and stuff, right? It relates the radius to the arc length. So just remember this, the arc length is some angle in radians times r. Okay, now that we have this equation, what are we going to do? We don't want just the arc length, we want how that thing is changing with time. I'm going to just rearrange this. For some reason they always put r first. Okay, so velocity, change in position over change in time, change in this length over change in time, and this arc length, that's equal to r times theta, okay? Like 2 pi r or pi r, this is just, it's the length of that little chunk. If we have a circle and that radius is not changing, and we'd have to take the derivative of each of these if we have a changing radius, but let's take the simplest case first. If the radius is not changing, and then all we have to worry about is how the angle is changing with time. And you can write this as d theta dt or put a dot on front of it. If you haven't seen that nomenclature before, all that dot means is we're taking one derivative with respect to time. So here's another definition for velocity for a circle. So velocity is equal to r d theta dt. And this little quantity here of how the angle is changing with time, we're going to call omega, and that is known as angular velocity. So not just regular velocity, angular, angle. It's how the angle is changing with time. And you can combine angular velocity with the radius to get your tangential velocity. So this is going to be like meters per second versus radians per second. And you go back and forth between these two with the radius of your circle. If we can figure out what velocity is, what's acceleration? Well, that's just one more derivative, right? So acceleration is very similar, radius, and now we're taking the second derivative with respect to time. And in this case, we're going to call the second derivative alpha. This is angular acceleration. So not just like meters per second squared, this is how the angle is changing with time. Alpha kind of sounds like A, right? Alpha and A go together. Omega, it's like two V's smushed together, I guess. So omega goes with velocity, alpha goes with acceleration, and it's the angular piece of it. So r omega and r alpha. Remember that your angles are going to be in radians. It's not 360 degrees times r, it's 2 pi r. Pi r, it's radians times r. In summary, velocity is always tangent to the curve. It's always in the tangent direction. There's nothing in the normal direction. That simplifies it. The equation for velocity, again, we're going to indicate the direction here is tangent, and v is equal to r omega if you have a nice simple circular path where omega is the angular velocity, how fast the angle is changing with time. Acceleration. Acceleration has two components. It has a tangential component and a normal component. These two components, here's the equation for it. The tangential piece, This is how much the magnitude of the velocity is changing. This is the direction of the velocity and how much. So if we go from 10 to 20 miles per hour, that magnitude changing, that's the tangent piece of it. We also have a normal piece of it, and this is describing how the direction is changing. This particle has to keep getting pulled to the center, pull to the center. So the direction change is towards the center in the normal direction. The tangential piece of it is the magnitude. We can also rewrite the acceleration equation in terms of angular acceleration and angular velocity. So dv dt, this turns into r alpha. That's the tangential piece of it. V squared over r, if we say v is equal to r omega, okay, so we have r squared omega squared over r, the r's cancel and you end up with r omega squared. So these two guys are the same. This is the normal piece of it, or you might see r alpha. These two guys are the same. This is the change in magnitude. There's an optional lab that you can do at home if you want to get more of an intuitive feel. Sometimes it helps to have a physical object and play around with it and actually feel the tug of these forces. So all you need for this lab is just a ball or stuffed animal or some object with a mass, and you're going to tie a string on it, okay? And then there's a couple different ways that you can create circular motion with your object on a string for this first exercise, and you don't actually have to tie the string to a pole. You're just going to hold it above it. Here I have a yardstick on the ground, and then I'm holding the string up in the air above the yardstick. I'm using the end of it as the center of my circle, and I'm using the yardstick to measure what my radius is. And you can also measure the length of your string. So if you know the length of your string and you know the radius, you can figure out this angle. Draw a free body diagram of it. You have a tension here. That tension is created. Part of the tension is mg, so just break it into vertical and horizontal components, okay? So the vertical component is coming from holding up the weight, but then there's this horizontal component, and that piece of it comes from changing the direction of the motion, okay? That v squared over r. So you can swing this tennis ball around in a circle, time it, get the velocity, you know the circumference, you know the radius, so you can do a change in position over change in time. Let it go for like a whole minute. So just pick a constant radius, a constant velocity, and count. 1, 2, 3, 4. It goes around 10 times in 15 seconds or something, or 20 times in 30 seconds, and you can get the velocity of it. So if you can find the velocity of it, you know the radius, you can measure the mass of it. If it's something like a tennis ball, you can look up the mass of a tennis ball online or use a kitchen scale or something. If you have the velocity, what I want you to do here is pretend like you don't know what gravity is. And gravity actually changes from one spot of the Earth to the other. The Earth is not perfectly spherical. So there's different values of gravity depending on where you are. So pretend like you don't know what gravity is, and you're going to use velocity, your radius, just the dimensions, and your unknown in your force balance is going to end up being your gravity. And you can measure what gravitational acceleration is based on the angle your object makes as you swing it in a circle. So that's kind of a fun thing, and we've actually got some pretty accurate results from this experiment in the past. So try it out. And again, this is all just an extra credit bonus assignment. You can turn it into the Chapter 11 homework box if you decide to do it, and I'll give you some bonus points towards your test if you try these guys out. So that's one exercise you can try out. Another thing you can do is take your object and swing it in a vertical circle. So up over your head and down. And this is going to help you really visualize those Ferris wheel questions on the last quiz. So if you swing that tennis ball around and you'll feel how this tension changes as it goes around. What's the tension at the top? What's the tension at the bottom? How fast would you have to spin it to keep water from coming out of the bucket? So you're going to be drawing a bunch of free body diagrams for here. You've got gravity going down and then that V squared over R, V squared over R. Why is there tension in the cable when you swing this around? The only reason there's tension, you're keeping it from going in a straight line, okay? That object wants to, an object in motion wants to stay in motion. It wants to, and the motion it wants to stay in is not just the magnitude, it's the direction. The object wants to keep going in a straight line direction, and you have to keep pulling it back in and pulling it back in to keep it from going straight. So you'll feel V squared over R as you tug it around, and you'll see how V squared over R really does change with velocity. If you swing it faster with a larger velocity or slower with a slower velocity, you can feel the V squared over, and it's really velocity dependent. V squared, it's not V, it's V squared. So play around with it and actually feel that force. Forces are, they're something you feel. You can't see it. You can't measure a force with a ruler. Force is a feeling. It's a push or a pull. It's a physical feeling, which is, we're used to using our eyes to experience things, but the units, we're using all of our senses, right? What does it smell like? What does it sound like? What is it? And for force, we experience force through what it feels like. So getting something and actually feeling it, that might help you start understanding a little bit better this rotational motion stuff. So try it out. It's very simple experiments. Last little piece. Okay, so you remember our constant acceleration equation. This is linear motion. We have change in position. We have our velocity. Linear versus curvilinear. It's going to be the same thing. Instead of velocities, we have angular velocity. Instead of acceleration, angular acceleration. Anytime you see an x, replace your x with an angle. So you're looking at how your position changes. Now you're just looking at how your angle changes. It's the same equation, right? 1/2 at squared, 1/2 alpha t squared. And you can get here in the same way. And so everything that you learned in the linear situation, you can now apply to curvilinear motion as well. The most complicated situation. This is the very end of the chapter, and this is where we're going to look at where the radius is changing as well as our r omega. This is the piece we had before. If we have a constant radius, then circumference equals 2 pi r. Arc length equals r theta. And then if we look at velocity, velocity is r d theta dt. This is the piece, the tangential piece that you're familiar with. That came with a caveat though, and that was that the radius was not changing in that state. So what happens when our radius is changing too? Then we have to add on how the radius is changing. So our velocity ends up getting two chunks to it. It has what you're used to, kind of the tangential component, only now it's not quite tangent anymore because our curve isn't quite a perfect circle anymore. So we're just going to call this theta. And theta is perpendicular to our radius. So we have how the radius is changing. So something in the radial direction, just draw a radius. And then we have our old familiar r omega, our r d theta dt. So these two components, and you're doing vector addition again. So we're going to add together the theta direction with our radial direction. And when we add these two chunks together, there is our overall velocity. Okay, so if velocity has extra stuff in it, our acceleration is going to definitely have extra stuff in it. Okay, what do we remember from last time? So we have r alpha. This is the change in magnitude. This would be the tangential piece. It's now not quite in the tangent direction, but the same idea. So we still have r alpha, but now we have a new piece that's created from our radius changing. And again, we have r omega squared. This is v squared over r, or r omega squared. This is what you recognized from before. This is in the radial direction or the normal direction. But we're going to add on to it the piece of how that radius is accelerating. So if we're actually accelerating in the radial direction, we're going to add this new piece onto it. And take this equation one chunk at a time. So you might understand what's going on in the radial direction, or you might understand what's going on in this direction. And just like you add up everything in the x direction, everything in the y direction, just one piece at a time, and then add it all together. Here's a big derivation of everything in that acceleration equation, and if you're interested, study this in the notes. The main gist of it, here's our velocity. So velocity isn't just r omega anymore. It has a tangential piece and now a radial piece. That radius is changing with time, as well as the tangential piece changing with time. And when we take the next derivative, okay, so this is our velocity, taking the next derivative. So we have two pieces here. We have to take the second derivative of r, we have this unit vector change in here, and then this one has 1, 2, 3 pieces. So again, we're looking at radial changing with time, and then theta changing with time, and then the direction changing with time, and there's some substitutions in here. And eventually you can get to this little piece. Get an equation sheet in front of you and write these equations on there. So, but this is the main gist of it. So just keep track of this equation if your radius is not constant. So there's 2 pieces to your velocity and 4 pieces to your acceleration that you have to add all of this together to get the overall picture for a changing radius and changing angle problem. Our last example, here's an example where we have the radius is changing and the angle is changing. This is kind of the worst case scenario. Let's read through the problem statement. Rotation of the arm about O is defined by, so they're giving us an equation for what the angle, how the angle is changing with time, where theta is in radians and t in seconds. Collar B slides along the arm such that r is equal. So we're given an equation for what the radius is doing with time and an equation for what our angle is doing with time. After the arm has rotated through 30 degrees, find the total velocity of the collar. So now our velocity is going to have 2 components, the radial and the angular components. We're also going to find the total acceleration of the collar. This time we're going to have 4 different components to walk through for our acceleration. And we're going to look at, let's see, relative acceleration with respect to the arm, as well as the total acceleration with respect to O. Modeling and analysis. So we have an equation for how the angle is changing with time. This is going to be in radians and in seconds, and we're going to evaluate this when theta is equal to 30 degrees. If we have the equation for the radius, we can take derivatives. So here's the position, radial velocity, radial acceleration. Here's our angle, angular velocity, angular acceleration. We're just taking derivatives with respect to time to go from position to velocity to acceleration. Angle, angular velocity, angular acceleration. It's the same idea. And these are the pieces that we're going to be plugging into our velocity and our acceleration equations. So here's our radial velocity. That's just how our radius is changing. And here's our angular velocity, r omega. So this is how it's changing. This would have been in the tangential direction. It's not quite in the tangent direction anymore. And to get the overall velocity, it's a right triangle. So a squared plus b squared equals c kind of a deal. So the overall velocity is a combination of these 2 pieces of it. And you can get the direction of the velocity and you can plug in to see what it is at some specific position. Acceleration. We have a radial piece of acceleration and an angular piece of acceleration. And we're just going to walk through that equation. So we had an equation for our angular radial, what was going on here. We also had an equation for what our angular velocity was that we can plug in. So you just walk through each piece of this equation and find what each part of it is doing. And you're going to have to be given a little bit more information for these types of problems, but you'll be given enough information to find each piece of the accelerations and each piece of your velocities and add those two pieces together. So overall velocity at some point you can find, overall acceleration at some point you can find. And then if you want to know with respect to O versus with respect to the bar, well, with respect to the bar, that would just be everything in the radial direction. Okay, hope that wasn't too confusing. I know this rotational motion stuff, it tends to be the hardest part of dynamics. So let me know what was confusing. If you want to watch a longer video, if you want to see some more examples, and there are more examples in the notes. I don't want to give you too much to just overwhelm you, but let me know where things are just not working out. We'll see you next time.